So, in today's lesson, we'll be talking about the differential calculus. So, before we get into this differential calculus, we must be aware about this slope. This slope, let's say, slope is all about finding out the rate of change over 2 points on the curve. Let's say I got a curve saying that I have x and y axis, and I have a curve that goes this way. And if I want to know the rate of change or the average rate of change of the 2 points, let's say x1 and x2, I should know the average rate of change. That means how my output is behaving with respect to my input, change in the output with respect to change in input. In this case, usually we are aware of one of the values, like we know this one. Let's say this is like around 2.2 comma 5, and we don't know what is this point, so let's take x2 and y2. If we know this much of information, we can able to understand what is the rate of change of this curve, what is the direction of this curve, and whether this curve is increasing or decreasing. What I meant here is the steepness of the curve. So we got three information when it comes to that thing. One, when the slope, we got the change in y-axis with respect to change in x-axis. If the slope is less than 0, which is negative slope, which represents there is a decrement in the steepness. That means when, let's say, this curve is decreasing as it moves further, so the slope will be here is negative. So the same way, when slope is greater than 0, when your curve is increasing between 2 points, let's say I'm going to take one more point here. Let me take it as x0, in the middle of, in the range of, let's say in the finite intervals of x0 to x1, what's happening to my f of x? F of x is increasing, so the steepness, which is my slope value, which is positive, that's why we can able to expect there is a positive slope. So this is what an intellectual understanding we should have over what is the slope. Slope usually an average rate of change between the 2 points over the curve. Let's say you got these 2 points, and these 2 points are enough to understand the behavior of the curve, whether it's decreasing or increasing, or no no changes at all over that thing. For example, let's say you have a curve saying that y equals to some constant value. Let's say this curve, I mean, this straight line represents y equals to 3 something. Here, the slope is 0. That means there is no changes when it comes to the graph. Whether you take from x1 to x2, within this finite interval of x1 and x2, there is no slope. No slope represent 0. Not positive or not negative. We got three conditions when it comes to this slope format. So the formula to find the slope is given in such a way that slope equals to change in y-axis, so which is nothing but the difference between the highest value and the lowest value over the curve. You need to make sure not x and y values alone, over the curve. So over the curve, we'll be having y and x coordinates. So y2 minus y1 divided by x2 minus x1. This is a formula to find the slope of the curve given points at the given point. So with this information, we can move on to the next concept, which is the differentiation. Okay, we call this thing as derivative of a curve at x equals to some constant. What I meant here is we just learned what is a slope and how we calculate the slope of a function. When it comes to the derivative, is most often like the same thing, but the only difference between a slope and the derivative is the slope gives you an average rate of change. When it comes to the derivative, it gives you the instantaneous rate of change. So let me take an example. Let's say you're driving through the car. This car is moving through certain points. So when you're moving through the car and you're going through a straight line, there is no slope at all because there is no changes you're taking. But the moment you start to move towards certain directions where it has curves, like you're going straight and taking a U-turn and going further and taking, there is a undefined curve where we need to pass through this thing. So, when you're traveling with this particular path, if you go through certain an interval of time, let's say from a point A to point B, if you're calculating how is your behavior of the car's direction, then you're finding the average change that you're making here. So the average rate of change that's going on with this within this interval is something like to the left and to the right. So let's say you're going to the left with a speed of some. So you're gonna randomly take how much of kilometers like you have traveled, or let me say this thing at point A, you're at 0 kilometers, and at point B you have reached around 20 kilometers, and it took around 10 minutes to it's too unrealistic. So let me take this thing 25 minutes to travel. So the average rate of change that's happening here is for the 20 kilometers and you're taking 25 minutes. So whatever the rate of change gonna give you this slope and the general direction of the car. When it comes to the instantaneous change, when you take the same interval and make this, the interval size is too low until approximately equals to zero. For example, if you take any point on this curve, let's say randomly point A1, at this point, whatever that you need to know about the car, what is the speed of the car, only at that given point, only at that point, and what is the direction of the car, and what is an average time you only took, like, so everything is instantaneous and everything is accurate. How can I do that thing is simply by drawing a tangent that touches this given exact point and finding an equation that represents the tangent and substituting the input, which is at that given point what is what is the speed or what is that input level. So here if you want to know much about the car, what you're going to usually do, like you're going to substitute at what speed you're moving through, and the moment you act on the speed, that what becomes an input for this derived function, which is your equation to the tangent. And that's what the next concept is, which is the derivative is nothing but the equation of the tangent of the f of x, or the curve. You're going to get a generalized equation when you start deriving the given function, and you call that as a tangent function. And the moment you substitute the requested or any point at that given input, so you're going to get the behavior of the entire function. For example, let me take f of x equals to sine x. In this case, I want to know what's going to happen to this sine x when x equals to 0, only at that point. So remember, what's this instantaneous change going to give us is simply, okay, we're going to have this equation saying that derivative of f of x equals to f of x plus h minus f of x divided by h. Sorry, this is going to go like as limit x tends to h. In this case, the sine graph starts from 0. Sine 0 is 0, maximum at 90 degrees. I'm going to go again back and a circular moment, it goes this way. So at that given point of x equals to 0, the tangent can be drawn this way. So this line, whatever the line that we are looking at, has a slope of 1. Slope of 1, which represents a positive slope, what is that thing represent is simply this given point, which is at x equals to 0, f of x is rising upward. That's again a positive slope. And the slope equals to 1, that represents the steepness. The graph. So let me take an example as a sine curve. Let me draw the sine curve. It starts from 0 and it goes on. So we're kind of coming from like this. Oh, it's a bad one. Let me draw this way. So at the point of 0, when x equals to 0, your f of x is also 0 for the curve of sine x. When x equals to 0, sine x and 0 is also 0. So the origin is 0 comma 0. We got this thing. Okay, but when I draw the tangent here respectively, this tangent will be having a slope of 1. So this is what I got when I do the derivative of sine x and then substitute the value of x as 0. But let's understand in more theoretical way how is this going to helpful and how is this make sense. Let's say I got a point when 1 is a known point. Let me use the slope formula. Slope equals to y2 minus y1 divided by x2 minus x1. I don't know the another point. Let's say I have some another point, some x2, y2. Let's take it as x1, y1. So after substituting here, let me just do this thing. The slope is 1 and 1 equals to y2, x2 are unknown. So I'm going to keep it as it is, but y1 and x1 are 0. So you got this one. So this says x2 times 1 equals to y2. In simple terms, let me take it as y equals to x, which is a straight line that passes through the origin. And obviously, this has a slope of 1. So this is a tangent. This is a tangent we are talking about. This is what this entire instantaneous change is trying to say is. In this case, if you observe it carefully, the point, the origin. For this instance, we took this x value as 0 as our input and we got a value of f of x, which is 0 again. So for this given point, the behavior of the point at that point only, nothing else. So in this case, according to the sine function, when you derive it, you're going to get, when you derive the sine function, what you're going to actually getting in simple terms is derivative is again the tangent line. The tangent line's behavior, and the only job of the tangent line is to tell you what is the direction and what is the slope for that given point is going to conquer. So that's it. For this point, the slope is maximum, which is m equals to 1. But the moment you find the slope of the next point, that might be a little shorter than the previous one. In this case, let me make use of this particular graph. I have this graph here. If you carefully observe this thing, so if I go with the origin, I have this maximum slope of 1. Sorry, the maximum slope is 1. If I move further away, and if you see, my slope is decreasing according to the tangent line. How this tangent line is moving towards. At the maximum point of my x equals to pi by 2, where my output is 1, my slope is 0. I wanted to focus on how each point has its own tangent line, and each tangent line resonates with one function that we're going to get once we derive the sine function. And that's the story behind how we do the derivative of the given function and how we make use of the derived function to find the instantaneous change of the input point at any respective point that we would like to know the behavior of the graph is about. But the question is, but the question is, Um, if you observe it one more time carefully, that for the same graph, let's say I have taken 2 points randomly, 2 points A and B. When I'm trying to find the rate of change of this graph, I can able to say whether this graph is increasing and what is the direction of this graph and the steepness of the graph. And that's it. That's what this slope is trying to say. When it comes to the derivatives, I'm going more precisely and I'm just zooming in a lot more to find what is the behavior of each of the point and what is the change that's happening with respect to the tangent that's attached to that given point. With respect to both output and input, I gonna get a particular point. This point gonna have its tangent respectively, and this tangent will gonna let us know that. Let me just shift it this way. Yeah, I think so. Yeah, each respective tangent is giving me an entire information about it. But what if I just make sure that the distance between these 2 points when I'm trying to find the slope becomes infinitely smaller? Let's say if I'm decreasing the distance between these 2 points, starting from changing the rate of change, which is the slope, the average rate of change here, when I make the distance between A to B, let's say the distance is h, and as limit h tends to 0, whatever the distance between these 2 points, let's say if this is A and this one is A plus h, let me write that B equals to A plus h. So according to the slope formula, so higher value minus lower value. So y2 minus y1 goes this way, f of A plus h, which is nothing but f of B minus f of A divided by A plus h minus A. I'm just making use of the slope formula, which is y2 minus y1, x2 minus x1. So previously we know this formula, but this is how we create this formula. When we make the distance between those 2 points infinitely smaller, almost equals to 0, what's going to happen to this thing is simply limit h tends to 0, f of A plus h minus f of A divided by h. This is a formula. This is an expression to find the derivative of a function at that given point. So what is this trying to say is, so when you draw these 2 points infinitely closer to each other, they are actually overlapping on each other, like almost. At this point, whatever the tangent line that you're facing, that will gonna give you a certain equation. And that equation you're gonna call it as the derivative of a function, the given function. For example, if of x equals to sine x, your derivative gonna be cos x. So the cos x acts like a tangent. This tangent have every information about the point. Every tangent that we're gonna looking forward to get can be decided by whatever the value that you're gonna give as an input to that derived function. And that's how you magnify the given graph or magnify the given function to understand what's happening to my input at whatever the points that I'm worried about, or whatever the points I would like to know more about. Similarly, whenever you're traveling to the car, wherever the direction you're going from point A to B, if you're getting a total speed, that's an average speed. That's like the total number of miles you covered divided by the time taken is what the slope is about. But imagine you're just going through this curve again, and if I say at the certain point, let's say at a point of C, in this given point, you are holding your steer, and at this point, you're gonna you're gonna have a tangent that says like, without even taking a turn, if you leave it as it is, what is the direction that your car gonna take? If you leave it as it is, your car gonna move this way, right? Instead of taking a curve, if you leave it as it is, this is more. So this direction, whatever the direction that is untouched by you, that is the instantaneous value of the sea. So this tangent gonna help you to understand whatever the direction of the sea, the point C, and speed. At that point, there is a huge difference between the instantaneous change and the rate of change. That's what they're trying to say when it comes to the calculus. When you take a deep look towards what you're doing, and when you're actually considering the only one point that you would like to know more about, that you're going to call it as a derivative of a function at a given point at x equals to some constant. And when you take a overall view about the curve, then you're going to call it as a slope. So obviously the slope has a relation with the derivatives, but at a precise way. It's like advanced version of the slope. That's what this derivative is all about.